Hello and welcome back to Physics Aid. Today we'll be taking a look at problems that have quite a momentous impact on your everyday view of life. That's right, we'll be talking about momentum, which for some reason is denoted with a P, and I still have no idea why. The main problem that arises when talking about momentum is the confusion surrounding elastic and inelastic collisions. We will be tackling that issue today and will hopefully clarify any uncertainties that anyone may have about it. But before we do that, I'm going to use this opportunity to explain how graphs should be read, because it is definitely one of the most important skills when taking the test. One important thing when reading the graphs on the AP test is that you can assume the shape of the graph when it looks very close to a specific shape. For example, if this velocity versus time graph looks like a rectangle, then just assume that it's a rectangle. Why in the world is this important? Because using geometry to analyze these graphs will actually save you a lot of time. In the laboratory, a 3 kilogram cart experiences a varying net force. The net force is measured as a function of time, and the data collected are displayed in the graph above. What is the change in the cart's momentum during the interval t is equal to 0 to t is equal to 2 seconds? Let's break it down a little bit. So the cart is having a force being applied throughout a period of time. But the only issue is that the force, as shown in the graph, is not constant. The force applied onto the cart keeps changing. But the good news is that, we can see a shape in the graph. If I recall from my younger years as a primary school student, I believe that is a triangle. If you have no idea where I'm going with this, I'll explain. Look at the vertical and horizontal axis of the graph. Force measured vertically and the passing time recorded horizontally. Now think about what the problem is asking for. The change in the cart's momentum between 0 and 2 seconds. What is the change in momentum? Impulse, which is also the mass of the cart times the change in velocity, which also happens to be the force applied to the cart times the amount of time it is applied. If F times delta equals t equals change in momentum, then that means that the area below the graph line must be the answer. It feels like a stretch, but it's really how graph reading works. Calculate the area in order to solve for the product of the axes. Using a rough approximation and the area formula for a triangle, I did 1/2 times 5 newtons times 2 seconds. That gives us the final answer, 5 newton seconds, which is the unit for momentum. So those are the basics of graph reading on the AP exam. There will be different variations depending on what they ask and what factors are included, but the general idea stays the same. Now, to explain elastic and inelastic collisions, I won't use a specific problem because understanding them is unrelated to problem solving. One fundamental rule of collisions is that momentum is always conserved, although it doesn't always appear to be that way. Ice cream falling and splatting on the ground doesn't appear to conserve momentum, but the Earth's mass is immeasurably greater, resulting in a seemingly negligible effect, although losing your ice cream has a significant effect on your mental health. So we know now that both elastic and inelastic collisions follow the conservation of momentum. Now let's discuss what makes each collision distinct from the other. Similar as to what would be expected of their names, elastic collisions resemble that of an elastic ball, while inelastic collisions resemble that of a, inelastic object. How can collisions like these both conserve all momentum? What makes them different from each other? Elastic collisions conserve all mechanical energy, while inelastic collisions convert the mechanical energy into molecular kinetic energy or thermal energy. However, it's not always this crystal clear about which occasions are elastic or not. A situation in which two balls bounce off of each other could be elastic, but not always perfectly elastic, especially in the real world. A question might ask you whether a problem is perfectly elastic or not. How you would solve these is by calculating the total kinetic energy of the two entities before and after the collision to see if there's a decrease in mechanical energy. In conclusion, momentum problems are not very difficult to solve algebraically, but you have to be very careful when considering the process by which you solve them. Conceptually, elastic and inelastic collisions are tricky to think about, especially when you're running low on time. Mathematically, the basic equations are pretty simple, but in certain kinds of problems you are faced with having to combine the equations to get the answer you need. So overall, for momentum problems, I would recommend practicing the derivations you need for certain situations, which usually have to do with the conservation of momentum. And that concludes all I have to say today, so I'll see you all in the next video.